All right, today we're going to do the big pulley assessment. So what we have here is we have a large pulley of mass, we'll call it big M, and then we have two small weights on the pulley. This little green one here is, we'll call this M1, and this big blue one here we'll call M2. So, because this one's larger than this one, the whole pulley is going to accelerate. This one's going to accelerate down, this one's going to accelerate up, and this pulley is going to have some angular acceleration in the clockwise direction. So the whole goal here is to see if we can create an expression or find a value for the acceleration, the linear acceleration of either of these two. Again, this one's accelerating down and this one's accelerating up. So the first step is to draw force diagrams, and we're going to need three. We're going to need one for this mass, one for this mass, and then we're going to need one for this big rigid object, this pulley that's free to rotate. And so implicit in the problem is that there's no friction between the pulley and its pivot point, but there's plenty of friction between the string and the pulley, which is going to make it rotate. So let's start off with some force diagrams. First force diagram we're going to draw is for this little one here, and we know that obviously the Earth is pulling it down, and we're going to call this one M1G. That's the weight. Now, there's a string pulling it up, and because the acceleration of this is in the up direction, this force by the string here, which we're going to call T1 for tension in string 1, has to be bigger than M1G. If we draw a force diagram for this M2 here, obviously the M2G is bigger than M1G, so let's make it bigger. So this is the Earth pulling it down, we'll call that M2G. And then what about this tension from this string 2 here? Well, interestingly enough, it has to be smaller than M2G because this block is accelerating down. But at the same time, it actually has to be bigger than T1 because this whole pulley has to rotate in this clockwise direction. So when we draw this, it weirdly has to be greater than this one, but less than this one, T2. Now for the pulley, because the pulley is a rigid object that is free to rotate, okay, we're going to draw it in such a way that we can look at the forces on it. So here's the pulley, rigid object free to rotate. Now obviously the Earth is pulling it down and this support is pulling it up. But because it's not accelerating up or down, I'm actually going to ignore those forces. And what I'm going to draw is I'm going to draw the forces that are causing it to rotate. So it's the forces that are causing it to accelerate. And what I have over here is I have T2, which is this one right here, causing it to rotate that direction. And then we have T1 over here. Now by itself, it would cause it to rotate in the other direction. But we can see that those are in opposite directions, and since T2 is bigger than T1, it's going to have a net unbalanced force in that direction. And each of these supplies its own torque also. So this is obviously at radius R, and this one over here also at radius R. So the next question says, calculate the actual acceleration of the masses. And so if I'm going to get the acceleration of the masses, it seems to me I have to do a Newton's second law statement for this one, a Newton's second law statement for this one, and a Newton's second law statement for the torques on this one. So I think what we should do is we should start with the let's start with the unbalanced forces here and see what we can discover. So let's do the M1 first. So when I think about the net unbalanced force on number 1, I know it's equal to M1A. If I look at the force diagram, the net force on 1 is equal to, well, it's accelerating up, so it has to be T1 minus M1G. Therefore, M1A has to be equal to T1 minus M1G. I think at some point I'm going to need to solve for the T1. But let's just leave it like this for now and go on. If I do the net force on block 2, this one is accelerating down, so it's M2A, the net force on block 2. This time it's going to be equal to M2G minus T2. Therefore, M2A is equal to M2G minus T2. Again, if I need to solve for the tension 2 and tension 2, I can put them in here in a moment. They may or may not be important. Now, what I'm going to do is I'm going to use the pulley, and I'm going to solve for the net unbalanced torque that's on there. So when I think about torques, I know that the net torque, just like net force is equal to MA, net torque is equal to I alpha. If I express the net torques on here, I know that the T2 supplies a torque and the T1 also supplies a torque. And what's nice is those are at 90 degrees to the radius vector. So basically, I have RT2 minus RT1. So this means that you have the torque provided by T2 minus the torque provided by T1. If I set these equal to each other, I alpha is equal to RT2 minus RT1. So in this statement, there are no A's, even though that's what I'm solving for. But if I substitute in T2 here, that's in terms of A. If I solve in T1 here, substitute in T1 here, that's in terms of A. And if I look at this I alpha, I can get this in terms of A also. So with a couple substitutions, I think I might be able to get to the promised land. So let's do some work here. We know that for a object that's rotating, if I want to find the linear acceleration, it's equal to R alpha. Therefore, alpha is equal to A over R. That's a substitution I can make right there. And it says here that this is hung over a large pulley that acts like a solid disk. So I, for a solid disk, okay, you can look it up in the book or you can ask your Googler, is equal to 1/2 mr squared. And so what we can do now is we can start making our substitutions in here and see if we can't simplify a little bit. So put the I in, so I have 1/2 mr squared times A over R, that's for the alpha, is equal to R, and then I have T2, and then I have RT1. So if I go back and solve for these, T1 is equal to M1G plus M1A. Cool. And then minus T2 is equal to M2G minus M2A. And hopefully this is a little bit more simple. When I actually look at this, I have R squared over R, so one of those two R's cancels there, and then it can cancel and magically disappear with all those R's there. So it turns out that all the R's magically disappear, which is really fun. So if I rewrite that then, I have 1/2 big M A is equal to M1 G No, this is an error. Let's go again. So we have RT2 minus RT1. Here, T2 is equal to M2G minus M2A. Minus R times M1G plus M1A. Okay, let's go from there. All the R's magically disappear, and you're left with MA is equal to M2G minus M2A minus M1G minus M1A. So what I have now is I have three terms, 1, 2, 3 terms with A in them, and I'm going to get them all on one side and then solve for A, and we'll see if we can develop an expression for that. So I have 1/2 big M A plus M2A plus M1A is equal to M2G minus M1G. Factor out of A. And now, looking at this expression, what I see is that I have values for M1, M2, G, and big M here. And if I plug those all in, I should be able to solve for A. So let's do that up here. According to the problem, so it says that M1 is 50 grams and M2 is 100 grams. So it says this one over here is 50 grams and this one is 100 grams. So, but we can't work in grams, we have to work in kilograms, which is annoying, but important. So, and the big M is equal to 1 kilogram. So when I go to plug this in, M2G is 2 minus M1G is 0.5, and divide by 1/2 of 1 plus 0.05 plus 0.2, and acceleration is equal to 2 meters per second per second. So that's going to give us the linear acceleration of this one in the down direction and the linear acceleration of that one in the up direction. The last thing it asks us to do is to solve for the tensions in the strings. Well, what's nice is I have a statement for tension here and a statement for tension here, and if I know the acceleration, I can go back and I can plug in here and we can get those values. So let's reset. So to the first one, according to this, T1 should be equal to M1, which is 0.05 times G, which is 10, plus 0.05 times acceleration is 2. So this is 0.5 and this is 0.1, so this is 0.6 newtons is T1. If I look at T2, according to T2, it's equal to m2g minus m2a. So T2 is equal to 0.2 times g is 10 minus 0.2 times a is 2. So this is 2 minus 0.4, which is 1.6 newtons. I like this solution because in our conceptual framework, T2 had to be bigger than T1. And if T2 is bigger than T1, the whole thing should accelerate this way. And if you look at our problem, T2 is definitely bigger than T1.